Hello and welcome back to Introduction to Data Science with R for Social Scientists. In this session I want to cover some special data types, namely strings, factors, dates and datetimes. Now, unlike the first couple of sessions where you learned to transform data and visualize data, you won't need the skills that we learned today for every single data science project. However, when you come across some of these data types, you would run into trouble if you don't know the basics about how strings or factors work. So this is what this session is for, to cover these basics. So let's start with strings. We've already seen strings a couple of times, and notably in the very first session where I gave you an overview of the different windows in RStudio and showed you how to run your first R code. Specifically, we printed the string hello world. Now, what are strings? So strings are defined as sequences of characters, which can be a word, a couple of words, it could be emojis, or it could even be numbers. Why would you save a number as a string? Well, in some cases you want to communicate that the number isn't actually a quantity or a count, but it rather represents something else. For example, a telephone number. And in a telephone number, it makes sense that you can't do any math with it, which is a common feature of strings. And when we multiply this with 3, for example, we get the error that the telephone number is a non-numeric argument, which totally makes sense because what would it mean to have 3 times the same telephone number? You can create strings or character vectors by surrounding a character or a sequence of characters with quotation marks. So the first problem you would have when creating a string is if you wanted to use a quotation mark inside a string. So one option that the book showed you to solve this problem is to wrap your string in single quotation marks. Then it is actually no problem to have quotation marks inside of quotation marks. However, I would argue that you shouldn't mix the double quotation marks with the single quotation marks. What you should rather do is escape the special characters. So you escape by using a backslash, and as you can see, the result is the same. It is also worth noting that R can deal with pretty much any language that you throw at it. You can also use the special characters and sign of these languages. So here are 2 characters that only exist in Germany, the special S character and the Ö character, so the O with the 2 dots above it. Now, as I said, R can deal with pretty much any language and any set of characters that you throw at it, but it doesn't always work. So I did a little experiment on my Windows machine by reading in different languages, and I start with Polish, then I go with German, Russian, and as you can see, the characters are displayed completely normally. However, when we come to Greek, we see a couple of hiccups. It doesn't work as intended, rather it converts one of the characters to a Chinese symbol for some reason. R and especially RStudio have become a lot better at dealing with foreign languages though, and in the last couple of years I've seen that problems with German have completely disappeared, and I'm sure that in one of the next updates you won't see these problems at all anymore. If you have a language that isn't really supported right now, you do not have to enter the data right here. You can also use the readLines function. And what readLines does is to read text or strings from a file, and depending on what text editor you use, this can be a safer option. So on Windows, for example, I like to use the text editors Kate or Notepad++ to enter strings. Here I use this generic text editor, and let's copy in the Greek text and save it to our project location. And here this works now. Also note that RStudio, so the driver console for the actual powerhouse that lives underneath, which is R, has more problems with encoding of different characters than R itself. So even when you see some weird printing issues, that doesn't necessarily mean that the actual string is corrupted. Sometimes it just means that RStudio doesn't know how to display it. But if you save it using write lines, so let's try this. And let's temporarily save this in an object. And now what we can do is to save the string vector as a new file. Let's call this Greek2txt. And this is how you write a string to a file or a character vector to a file. Now, the main topic of the strings chapter in the book is about regular expressions, but before we talk about regular expressions, I want to talk about a couple of functions that were also mentioned in the book, but I thought that they were ordered in a little bit of a weird way, and I would instead discuss them in the order of the most to the least useful of these functions, even though there are a couple that are probably on the same rank. So let's first talk about string detect. And the reason why I think string detect is quite powerful is because you can use it very easily with the filter command. So let's get a data set in here. Let's use flights and have a quick look at flights to remind ourselves how it looks like. So for example, if we wanted to find planes where the tail number starts with a D, we could use string detect. Let's start with the flights data set, then use filter, and inside of filter you can directly use string detect. And then here in the little pop-up you see that what goes first is the string, then we want to add the pattern, and this will form our condition for the filtering. So the string that we want to use is the variable tail number, and what we want to have is all the tail numbers that start with a D. So what I'm doing here is using a simple string that is D, but I also want to use an anchor. So the two anchors that were mentioned in the book are the beginning of a string and the end. I'm using the anchor for the beginning, which is this little head character. And when I run this now, I get only the planes that start with a D. I get only the planes where the tail number starts with a D. When we take a step back and look at it with the example from the book, so we have a simple character vector here, X, which contains the words apple, banana, and pear. And what string detect does is it returns a logical value, so either true or false, for every element in this vector. And it determines if the value should be true or false by looking for a character or a substring of the strings in the string vector. So when I run this now, I get the results true because E is in apple, false because there's no E in banana, and true at the end since there is an E in pear. And as you should remember, this is exactly what filter expects. So whenever a condition is evaluated to true, it keeps the observation, it keeps the row from the data frame, and when the result of the condition is false, it removes this observation from the dataset. Then next I want to talk about str replace. And I think that this is probably the second most important function when it comes to strings, because it helps you to quickly change a couple of strings at the same time using a pattern and a replacement. So let's look at our simple example again. add the X, and what we need to input here now is first the string again, then the pattern, and then the replacement. So the pattern in this case, we can again use E, and as a replacement, we can simply use A. So what's happening here now is that every E in here is replaced with an A. And the reason why this is so important for data science is because we can quickly change the values of a variable on the fly. So let's look again at the flights data set. And let's say we actually wanted to have the city name instead of the abbreviation for the airport. So what we could do is we could mutate and create a new column called city. And what we could do here, with str replace is we could say that whenever it encounters in the destination the string ATL, then it should replace this with Atlanta. And here we go. In our new column, we now have the information that ATL is really the city of Atlanta. So one time where this function would have been useful was when we were talking about the penguins dataset. And as I mentioned, the species names there are quite long. So we had Adeline penguin, Gentoo penguins, chinstrap penguins, and we could have simply used str replace to replace the word penguin with, just nothing, for example, because it's actually just repetitive and it didn't add any value to the species names there. So then this is why I think str replace is the second most important function from the stringr package, which delivers these string manipulation functions in the tidyverse. Then the third most important function is strc. So here we have basically a variation of the concatenate command that we already know and use, for example, to make the X object up here. And what this does is to put each of the strings inside of it in one element, but it keeps these elements separate. What the strc command does is to transform the elements inside into one. And there are two more important arguments to strc, which are the sep argument, and sep specifies a separator. So for example, you could want to have one string, but each of the elements that you input should be separated by a comma and a white space. And then the second important argument is collapse. And at first sight, that doesn't seem to do anything because it expects a slightly different data structure. So it expects a vector rather than several separate inputs. And then it is doing exactly the same. So as you can see already at first sight, strc looks quite simple, but because of the different behavior that you get when you either input individual elements or a character vector is what makes this a little bit difficult. So let's look at another example. Let's have just apple and banana in a vector, and then let's have peer outside of this vector in a separate input to the function. And then let's use the separator comma just to make it better visible where the transition happens. So what you get now is a new element with the length of 2, where you have first apple and pear and then banana and pear. Why did this happen? The reason is that strc is vectorized, which is a fancy word that means that every single element of an input gets concatenated with the elements of the other input. So let's say the other input wasn't just one element long, but it was 2 elements. And let's call these pineapple, and I leave the pear. And what's happening here now is that apple gets joined with pineapple and banana gets joined with pear. So as I said, this quickly becomes difficult, and I would suggest that you try it out yourself to see how you can wrap your head around it. I often myself still have to try if I actually want a separator or the collapse command, because if I used collapse here and did this with the same value for the collapse argument as for the separator argument, then I would get this result here, and as you can see, it combines the two logics that we've learned here above. Then next up we have str split. And this is one of the functions that you won't use quite as often, so it is further down in the list. So let's use this as an example. And if we now use str split on y, and here it expects again the string first and then a pattern. And as the pattern, I choose the same value that we used for separator and collapse. And what it does is to split the string into individual elements. Now, when you look at the indexing here, you see you have a 1 in 2 square brackets and then a 1 in 1 square bracket. This means that str split actually creates a list. And that can be a bit of a hassle to work with, so I wanted to quickly mention another function from the tidyr package, which is part of the core tidyverse. And to do this, we can wrap the string in a tibble, and we can use an ID here, which is simply 1, and then our string, which is simply the y object. And then if I use mutate now and use str split, the result will look very strangely, because what you have here now is that you actually have a list within the column called string. And to get rid of this, tidyr has a function called unnest, and it takes as an argument the column that you want to unnest. And what happens now is that you basically have the long version of the list, so each of the elements of the list is now its own observation, and the other columns in the table will be duplicated so that you have one observation here now for each of the elements in the list. Another function that was used in the book is str sub. And what this does is super simple. It takes as an input a string again. Let's use our vector of strings with apple, banana, and pear. And then it takes the values start and end. So let's say you want to start at the second position and end after the third. So what this does now is it extracts the second and the third character from apple, banana, and pear. Then what you might also sometimes need is str subset and str extract. And I would argue that those actually kind of belong together, so I'm talking about them under the same subsection. And I'm using again the X object that contains apple, banana, and pear. And this goes into the string argument. And then the pattern I want to use to subset is EA. So the output here are all elements from X which contain the pattern. And then str extract does something similar. However, it will have the same length as the input string vector, and it will return either the match to the pattern or an NA, and we will see in a little bit why this might be useful. And then a function that I almost never use is strcount, and it does exactly what it sounds like. So let's give it a quick test. Let's use the X object again, and we want to see the pattern E here, and it simply counts the number of E's that are in the elements of the string. So there's 1 E in apple, there are 0 E's in banana, and there's 1 E in pear. And then finally, there's a function that was used quite often in this chapter, but that is almost never used in practice, which is strview. And the reason for this is strview is mainly used as a tool to learn regular expressions and to learn dealing with strings in R. So once you have a basic understanding of strings, you will probably not use it. You will use one of the other functions instead. But for this particular session here, it is quite useful. So let's see how it works. And it basically just highlights the match of a search. So I was looking for the pattern E here, and you can see that the E is now highlighted in apple and pear. So let's get to the main topic of the strings chapter, and I'm taking a bit of a different approach here than the book, because I wanted to show you a page that was created by RStudio, and it features a collection of cheat sheets. So there's a cheat sheet for ggplot, ddplyr, tidying data with tidyr, and so on. And the one we want to look at is for regular expressions, which is this one here. It's called Regular Expressions, Basics of Regular Expressions and Pattern Matching in R by Ian Kopoka. And I think it's an amazing tool to get to know regular expressions. This is something that I actually put on my office wall while writing my PhD, because I found myself looking for this cheat sheet again and again and looking up some of the regular expressions on there. And then this is how the cheat sheet looks. We basically covered already the big part here with the different functions, and it has the stringer functions, but it also tells you about the same functions in base R. So for example, the grep function in R is doing actually exactly the same as str detect from string R. We are taking the stringer functions here because they are more concise. As you can see, for example, the pattern comes first in grep, which can get a little tricky, and it's also a little strange because some of the base R functions use the string first and then have the pattern second, and that is just a little confusing. So let's get started. I have RStudio on the left here, and I focused in on the view of our markdown, and I'm starting at the upper left corner of the cheat sheet. And what you can see here are character classes. Those are probably the most important thing with regular expressions. So I put together a couple of examples here. And let's say when we start up here, we want to look for strings that contain digits. So I'm using strview here, and we use the examples as the string. And then we create our first regular expression by using the D with the two backslashes. And it now highlights the first number it encounters. As you can see in the cheat sheet, we could also use digit, or we could actually define what we count as digits by using the square brackets and then the sequence from 0 to 9, which are all the different numerical characters. Next up, we could also look for all characters which are non-digits, which is the same thing but with a capital D. And as you can see here now, it always highlights the first character that it finds. Now we can also use strViewAll to show us all of the non-digit characters, and you can see these are actually most of them. Then we could look for lowercase characters, uppercase characters, alphabetical characters, so these are lower and uppercase characters. Let's quickly try this. So the result is almost the same, but the plus isn't an alphanumerical character, so it is actually excluded from the highlighting view here. Then we have word characters, which are all alphabetical characters and all digits combined, plus the underscore. So let's look for all the word characters. So as you can see, it is almost everything except the plus and the white space down here. If you wanted to look for white space, you can look for the S here. And it highlights only the white spaces in the telephone number. You can also include tabs in here if you look for blank instead of space, or you could look for not space characters, which is also sometimes quite interesting. So here it highlights everything but the space if this is what you wanted. And then we have the punctuation. And here we don't actually find anything because by default strViewAll only displays the first 6 elements of examples here. But what we could do is we could, for example, check one of the letter ones. So let's see the 8 one. And here the punctuation is actually highlighted. Let's see the 9th one. We see there are a couple of different punctuations here. And then there are a few more which I won't discuss here because I never used them before and I think they are useful in only very few cases. We can also look for special meta characters. For example, you can save a new line character in a string. So let's do this. And by default, it simply displays this as a new line character. But if we would use, for example, write lines, we see that this is converted into an actual new line. And sometimes within a string, the new line is saved, or you have a tab that is saved in there, or one of the others, and then you can look for this. So let's see, we could, for example, directly put this into our str view. And then to look for the new line character, we need to escape it. So let's escape this. And it shows us that the new line is just before the word new. Then we have lookarounds and conditionals. These are a bit more advanced, but just so you've heard of at least one of them, let's use the look ahead. And we can simply copy this. And let's see, in our look ahead, we want to look for new. So we see what we have here is the position just before new. So that isn't super useful, but let's say we wanted to have the last word character just before new. So what we could do here is to use again the word character. And then we also need to take care of the white space, which I simply add to the look ahead. And then let's remove the new line character from here because it actually just complicates this example. And then what we see here is that we can look for the word character which immediately precedes new. And if you did the same now with the look behind, you get the first character that directly follows the word new. So then let's scroll over in the cheat sheet, and what you get here are character classes and groups. So the first one is any character except point. And this is, I think, one of the first examples in the book because it includes all of the characters, and you might sometimes want to use this. So here, for example, it simply highlights all the characters in the first 6 examples, but you could, for example, want to combine this with the anchor that we already seen. And now it automatically selects the first character in every string in our examples object. We can again use the or character here to say we wanted either, let's say, a P or an A. So then it highlights both of these. We can also define a list of permitted characters. So let's say the permitted characters are A, E, and I. And these are not separated by a comma or anything. You just put them one after another. And now it highlights all of these characters. You can also use it to say the opposite. So if I do this, then the regular expression means that I want all characters except those 3. And as you see, it's the exact opposite. And then instead of square brackets, we could also use round brackets. These are meant for grouping, and grouping basically has 2 functions in regular expressions. The first one is mentioned here, that it enables back-referencing. And the second one is that you can use it like in mathematical operations to define other patterns. So let's say, for example, we wanted to look for P either followed by L or E. So we could use P and then L or E. So the or inside of the group means that the or character is only referring to the letters inside of the group. And as you can see, this worked perfectly. So for the back referencing, we need a different function, str replace, for example. And what we could want, for example, is to again look for P followed by either L or E. And then back referencing works by using 2 backslashes and then a 1, or if you have 2 groups, that could be a 2 or a 3. And what I want to do is I want to replace the P followed by an L and E by P followed by the letter which is in the group, but twice. So there we go. The letter directly following the P is now duplicated. Then we already talked about anchors. So the 2 most important ones are the start of a string and the end of a string. What is also often interesting is the edge of the word. So for example, if we use apple as the pattern here, then what it will do, it will highlight apple and the apple in pineapple. But when I use the edge of the word, it only looks for instances where apple is a complete word surrounded by empty strings at either edge of a word. And then scrolling over here, we have quantifiers. So as an example, we use the letter P. And if I look for all instances here now, it displays the 2 P's in apples and the 3 P's in pineapple. But let's say I wanted to match this exactly one time. So I could use curly braces and say 1. And now, of course, it still highlights all of them because now there are individual instances. So what I actually need to do is to define that it should be followed by something which is not P. So I use the list of permitted characters again. And as you can see, the result is still not only the single ends. So what we need to do is we need to combine this with a look ahead. And there we go. Now only the P's which are followed by a different character are highlighted. And as you can see, this has already become a bit complicated. So you can appreciate that building up your own regular expression can be difficult. Now let's quickly talk about the other quantifiers here. Matches at least 0 times. That might look a bit confusing because why would you want to match a character even when it is only mentioned 0 times? But again, this makes sense when you have a more complicated string. So let's say we wanted to look for a German telephone number, and the way we could build this up is we start with either a digit or a plus, followed by some white space, which is sometimes done in telephone numbers. Not here, but it sometimes is. So I want the white space. But since this is not always used in telephone numbers, I want to match it only when it is there. So this is why I use the star. And of course, the plus is also a special character, so we need to escape it. And this is my usual process here. I never know how often I need to escape one of these characters. So first try 1, then 2, and so on. And as you can see now, it matches the plus. So this is already good. And then next we want to have only digits. So I say digit character. So I say digit character or whitespace actually. And now it actually highlights the entire phone number. Then down at the bottom here, there is some more stuff. You don't have to pay attention to Perl true. This is only important for the base R functions. Since we are using stringer, it has no effect. But one thing that's interesting here is the fixed command. Because by default, all of the stringer functions use regular expressions, but maybe there's a reason why you don't want to use regular expressions. For example, if you use the fixed version of the functions, they are quite a bit faster. If you have a really long data set, that might make sense. Let's use string detect here, and we use the examples again. And then we have to wrap fixed around our pattern. So let's say the pattern we are looking for is +4, 9. And as I just shown you, the plus is usually a special character for regular expressions, but since we wrap this in fix, it is no problem. We can simply use it here, but on the other side of the coin, you can't use the anchor, for example, anymore. It now looks for an actual power sign, which isn't anywhere in these examples. While you're using fixed, you can still use ignore case though. So let's say you wanted to look for banana, but the pattern that you entered has a capital B. It doesn't find anything only when you use ignore case and switch it to true. Then it ignores the case and it also looks for banana when the actual capitalization of string and pattern don't match up. Then over here we already spoke about escaping characters. Case conversion only works with base R. It doesn't work with the string R functions. Instead, in stringer, you can use str to lower and str to upper to convert an entire case. So let's say we have banana here, and when we use str to upper, it converts this to banana. There's also the title case. So in English, there's something called title case, and it's the specific capitalization of titles. So for example, a chapter or a section title. And as you can see here, it capitalizes most words, not all of them. But in this sentence here, for example, it capitalizes each of the words, and there are some special rules where this doesn't happen. And then on the very right here, we have something about greedy matches. This can be quite interesting in some special cases, but it is a bit advanced and I couldn't come up with a good example besides the one in the book, so I would suggest you simply study this. So there we go. This concludes the short explanation of regular expressions. Obviously, this is a huge topic, and to be totally honest, I still didn't manage to wrap my head completely around them. There are infinite uses for it, but as the book also explains, don't try to solve everything with a regular expression. Sometimes it makes sense to break up the task into a few smaller tasks, and sometimes it makes sense to look on Stack Overflow instead of coming up with the perfect regular expression for your case. Often you find a good answer there, and someone has described a good regular expression that fills your needs. I would also suggest that you download this cheat sheet, and especially in the beginning, it probably makes sense to also create your own document, your own cheat sheet, where you save a couple of the important regular expressions that you find useful, that you come across, and just save them there instead of trying to memorize the different regular expressions that you might need at some point. And with that, moving on to factors. As always, it probably makes sense to make a few notes in your own chapter. I'm basically only providing these documents so that you have somewhere to start and that you don't have to retype the things that I type while recording these videos. But it makes sense to add some more examples that you find useful and to add some explanations to the examples that I put in here, because I leave you with the video instead of writing down my own notes for you. And with that said, let's move on to factors. Now, factors are not as important today as they used to be. The main reason why I wanted to cover them is that things get really annoying if you don't have an understanding of factors. So let's get started by creating a factor vector. For this, we need two things. We need some levels and then we need some values. What I chose here as an example could be the answers to a survey question. So you have different observations of people who say that they do something often, always, rarely, and so on. And in the levels, we have the possible responses. So in a Likert scale, there are usually 5 responses or 7, and you go from one end of the spectrum, which is never here, gradually to the other end of the spectrum, which is always. And then to create the factor, we use the command factor. And I already opened the help over here. So we first want to enter the responses and then our Likert levels. The tiny typo here. And now what we get is this view here. So we have our values on top, and then underneath we have the individual levels. So let's save this in a new object called responses factor, and we can print this again to see the same view. And to explain factors, there is a function which is called onClass, and we won't need this function again, but what it does is to helpfully display what the underlying data structure looks like if you remove the class and if you remove the special instructions on how to print a factor. So basically, a factor consists of the values here, which are represented as numbers, and then it consists of the attribute, the levels. And the way you can imagine this is you go to a Chinese restaurant and there is an item on the menu that you think you want to try out, but you're not sure how to pronounce it. So instead of ordering the dish, you order number 122, and what you get is the dish that you wanted and saw on the menu. The same thing happens here. So in our values, the first number is 4. So R knows that what the factor is referring to is the 4th level. So this is 1, 2, 3, 4. So the first value should be often, and this is true. The reason why R does this traditionally is to save some space. So if you can imagine, R is already a quite old language, and some 20 or 30 years ago, it really made a difference if you could save just individual numbers or potentially long labels for the values. So you were able to save the labels just once, and then you only save the index as the values in a factor. However, there are also some practical reasons today for using factors, and one of the main ones is that you can order categorical variables in a specific way, for example, for plotting in ggplot. But many people are also pretty annoyed by the behavior of R when it comes to factors, and here are just 2 examples that can be a bit tricky. So let's say you noticed that while entering the data, you made a mistake, and the 6th value should actually not be sometimes, which it is right now, but instead you want it to be often. So you use the square brackets here to index the 6th element of the vector, and then you want to assign often to it. And now what this does is to say invalid factor, because I misspelled the label, even though I wrote often in the correct way. But in the levels here, it is written with a capital O, so this did not work, and instead it now displays NA as the 6th element. So this could be seen as upside or downside, depending on how you look at it. If you do this with the correct spelling, then it works. And some people say that it absolutely makes sense that R displays a warning here and makes sure you type the values correctly. On the other hand, you might see the warning and be confused, because why would R check if your entered values are correct? Okay, so let's assign it the correct one here to get our original vector back. And so I know that this isn't used in the future. I set this to eval false, and now while knitting, this code chunk is ignored here. The second thing, which could be tricky, is when you convert factors to numeric values. And I have a little example here. So let's say you recorded the income in a survey and you got different replies from people. So there was one with a 10,000 income. Doesn't matter what currency this is. But when we have this as a factor now, and you can see I have this factor here, and I wanted to convert this to numeric, the result would not be what you probably expected. So what gets converted to numeric are not the levels, so the 10,000, 1,200 and so on, but it's instead the index, so the values of the actual factor. So I get 1, 2, 3, 4 here. What you would need to do to convert this correctly is to first convert the factor into a character vector, and then convert it to a numeric vector. So now you have the income properly as a numeric vector. You should be quick to spot this, but this is actually one of the few things that you do have to remember, because in larger data sets, what could happen is that you look at the vector that is converted here, so 1, 2, 3, and if the data set is long enough, then eventually you get some numbers that make sense. And even while plotting, you might not realize that you made a mistake. And if you have some 10,000 people in there and they replied with 9,000 different answers to the income question, then you probably won't notice if someone has the 3,000th value, which is then converted to 3,000 here. It kind of makes sense as an income, so you don't realize it until it is probably too late and you publish your results already in the worst case. So then what I did here was to create a factor without the levels, and we can also do this with our original responses to show you how this works. So we create a new object called response fct2. Oh. And now on first glance, this looks exactly the same. So we still have our same values up here. But what we have now is that the levels are in a complete disorder. So it starts with always, then there's never, often, rarely, sometimes. So the order is completely messed up. What R does when you simply enter the responses as a factor here is to order the factor levels alphabetically. And this, of course, doesn't make a whole lot of sense, but is something you find often in the wild, that you have a categorical variable that isn't a factor or that gets converted to a factor, and the order of the levels isn't particularly useful. And this is what the forcat package in the tidyverse is for. We can start with a simple function, which is fct in order. And the forcats functions always look the same. They start with fct and an underscore, so it's actually quite easy to look through the functions in the package, because as soon as you type fct and the underscore, you get all of the different functions from forcats here. So what we can do is we enter the newly created factor vector in here, and when we run this now, the order of the levels has changed. The levels are instead now in the order of the appearance of the values in the factor. It starts with often, then the next one here is always, then the next one is rarely, and so on. And the reason why this is still useful today is because of ggplot. Because ggplot uses the order of the levels to determine where to put, for example, bar plots of a categorical variable. So as you can see here now, we returned to the original vector, and I had to turn this into a tibble to make it possible to use it in ggplot. Then I'm simply mapping the aesthetics to x here. X is the first argument in the AES command. So responses is map to x, and then geom bar, of course, counts the appearance of the values of the factor and creates the bar plot here. And what you can see here is that the order of the levels is used. So we start on the left with never, which is the first level of responses FTC. And it makes sense in this case because the actual order increases from never using something to rarely, sometimes often, and always. So it honors this natural order that I put the factor levels in. And then something which I find a little disorienting, but what actually makes sense is when you want to flip this plot. So we use chord flip. And what happens now is that the first factor level is actually at the bottom. And at first glance, this often confuses me, but it makes sense when you think about what a y-axis would look like. If these were numeric values, then you would have the smallest values at the bottom, and when you go up the y-axis, they slowly increase. So then what happens if the factor is in a different order? So let's use FCT2 here, and when we plot this now, you can see that it uses the same messed up alphabetical order, and this time it goes again from the bottom to the top. So let's say we want to reorder this, and of course we could put it back in the original order of responses FCT, but maybe when we look at this, we think that it would make sense to order them by length. So to put the biggest one on top or bottom and then increase or decrease while you go up or down the y-axis. We can use another forcats function for this. And let's first copy the first line here. And we use mutate to change response. No, response. And here I want to use FCT reorder. And reorder uses two arguments here, which is the factor first, and then how you want to order it. And what we can do to order it according to the count is we first add the count in ourselves. When I run just this now, you can see that count doesn't change the factor. It still keeps it this way, but it adds the variable n, so the count variable. And we use this to order our factor. Pipe this into ggplot. And now as aesthetics, I use response for the x variable and then n for the y variable. Or you know what, let's do it the other way around. And then we use geom call this time because we already counted the values. So here we go. Now we have them ordered from tallest bar to smallest bar. If you wanted to do it the other way around, we could check the help file for this. And you can see there's an argument called desk, which means descending. And we can change it from the default, which is false, to true, to order the bars the other way around. Another thing that you could do is to simply reverse the order. So let's keep it that way and reverse it back to the original order, which we can do with fct ref, so which is short for reverse. And notice that we can directly put this into the aesthetics, so it gets converted on the fly. And the advantage is, or the disadvantage, depending on how you see it, is that we now have FTC reversed as the axis label here, and we're back to our original order. Then let's say you only wanted to move one or two of the levels, or you actually wanted to return to the original order. You could use the function fct relevel, and this again takes two arguments. So the factor and then the dots, we can use them to name our actual levels that we want to move. So let's say we wanted to move always. Always is currently the second one from the top here. And let's remove the reverse order command here. Let's see what happens. So now always is way on the bottom here because it's now the first level. If we wanted to change it to the last level to put always on top here, we can use the after argument, and then we want to have this at the last position. There are 5 levels, so we want to have always after the 4th level. And now it is on top here. We can also move a couple of levels at the same time. So let's say I also wanted to move often. And now we need to put this after 3. And then we have often at the top and then always afterwards. This doesn't make a lot of sense, so let's switch the two up actually. Yeah, so we have always, often, sometimes, rarely, and never. So we are actually back at the original order that makes sense by only moving 2 of the factor levels. And then let's say you wanted to change some of the labels here completely. We can do this using fct recode. The help doesn't give you a whole lot of information, but you can turn to the book here to see how it works. Make a new line, and then the new name of the level, comes first. Let's call this almost always. And then the name of the old level comes second, so let's call this always. And then to make this look a little bit better, let's do some formatting here. And when we change this now, we have almost always at the bottom here, and the label is different now. If you wanted to change more labels, you do the same thing. So almost never, for example, is the new label for never. And there we go. And then let's say you wanted to publish this in a newspaper, for example, and your editor comes to you and says, those are too many categories, people don't really know what they mean. Can't you do instead just a simple differentiation between people who say that they do something, so they answer yes, and people who say that they don't do something, so they answer no. So what we can do here is to collapse a couple of categories. And the function is called fct collapse. And here it works pretty much the same. So we first have the new category yes, and then we want to list all of the levels that belong to this new category. So it is always, often, and sometimes. And then the second category should be no, and it includes never and rarely. And there we go. Now we only have 2 categories. The example here isn't necessarily the only way you could separate these categories, but it is something that I've seen before, and just in case, now you know how to do it. And then the last function which was shown in the chapter is called fct_lump. And when we look at the help for this function, there is a little note here that says that fct_lump has basically been replaced by 4 different functions. So that is fct_lump min, prop, n, and lowfrag. And we can try out fct_lump here. So let's say we wanted 2 categories, but what fct_lump does is to reduce the seldom used categories into 1. So here we use response again. And then it tells us lumps all levels except for the n most frequent ones. So if we want 2, we want to lump all of the categories together except for the most frequent one. Oh, what's happening here? And this doesn't work because all of the categories in this tibble are actually mentioned just one, and fct_lump doesn't know what to do with this. We need to run this before running count, and I think now it should work. Yeah, now it put sometimes there as the most often used category, and then it lumped all of the others together into other, which probably doesn't make a lot of sense, but now you know how you would do this. I've seen this before when you have probably like more than 20 categories or so, and the first 10 or 12 come up again and again and again, and then the others are rarely ever used, so you lump them together. I would rather do this by hand and make it explicit which categories I collapse, so I would rather use fct collapse here. But in case you just wanted to quickly see what happens if you add up the instances of the seldom used variable, you could do this with fct_lump. And this concludes the section of the video that talks about factors, and we next move on to dates and datetimes.